Well, hi, I'm Robert Crowe. I'm a product manager at Google, working in AI for quite a while. And today we're going to be talking about JAX, and really JAX made simple, with a strong focus on how to make neural networks fast in today's world. I'm going to assume in this talk that you know machine learning and you've trained models. We're going to be covering a lot of ground really fast. So it might be a little bit of a blur, but I think it's important to give you the overall picture of really what the state of the art is in trying to make models run fast, especially during training. Don't worry, at the end of the talk, I'm going to give you links to a lot of resources so you can dive deeper into each of the topics that we discuss. Okay, so probably you know, Google has a long history in AI. We've been doing it for a long time, and starting with disbelief way back when, and then TensorFlow. We also invented the transformer architecture, which has had some impact these days. And we also created the first LLMs, which you may or may not know, but actually years before they were a big thing, we were using them internally. So then the question is, why would we invent a new framework, a new Python framework for AI, JAX? And the reason is because we needed it. We've learned a lot over the years, and we need to be able to run at massive scales. And we also need flexibility and modularity in the things we do, because we do a lot of research and exploratory work as well. We need to be able to innovate quickly. So for JAX, high performance, flexibility, and modularity really became the design centers for this new framework. And it turns out that JAX is not just a great framework just when you're working at like Google scale, but really in today's world, whenever you're working in AI, JAX has some incredible strengths, and we'll talk about a couple of them. Again, we're going to move really quickly. But the focus here is really on making things fast. I should also say JAX is not just used in AI, it's also used in a lot of kinds of scientific computing. So computational analysis for things like bioinformatics and genomics, and there's a long list of libraries that are built on top of JAX that take advantage of the speed of its numerical computation. So JAX is part of a complete stack of frameworks and tooling, but let's start with JAX itself. So think of JAX as not just another library, but a high-performance platform for doing numerical computing in Python. It builds on a familiar syntax in Python and NumPy, but it adds powerful capabilities through composable function transformations. So these are functions and decorators that you use and compose with other functions. So there's, for example, JIT, grad to calculate so JIT is just-in-time compilation. Grad to calculate the gradient of a function, VMAP to do vectorization of a function, shard map, which is used for very fine-grained sharding. And those allow JAX to automatically optimize your standard Python code for accelerators like GPUs and TPUs. And again, it's used not just in AI, but also in other fields of scientific computing. It's not just fast on one GPU or TPU, it's designed to scale. And scaling is going to be a central thing that we're talking about today, because that's really how you get things to go fast. You need to be able to scale up, take advantage of all the power you have in the compute resources that you have. So this is largely thanks to the XLA compiler, which is the layer below JAX that compiles your JAX code, your Python code, into machine code. and then does a lot of optimization. It does some automatic distribution, which you can take advantage of, and handles things like communication primitives. This also means that your code can scale well automatically, although there's a certain level that you get with automatic scaling, and then when you really need to optimize beyond that, you dive in and start hand tuning for getting the last few bits of performance out of it. It's also very portable, as we'll see in a second, so that's important for moving between environments or working with different teams. Scalability is really incredibly important. In today's world, you can't do a lot with just one accelerator or one CPU. This is a November 2023 study, and this goes to over 50,000 TPUs, which is certainly more than I've ever run. Probably most of you have not run that many at one time either. But let's take a deeper look at that graph. The ideal scaling would be the dark dots on top. And what we achieved with JAX is the lighter dots just below that. It's near ideal, really state of the art. On GPUs, the situation, by the way, that was with TPUs. On GPUs, the situation is similar. So again, we see really state of the art scaling. The measurement here we're using is effective model flops utilization, which is maybe a new term for you. But essentially, it's the ratio of FP8 flops divided by peak BF16 flops. So this achieves over 80% EMFU, which is state of the art. I should also say a lot of the reason we're able to do that on GPUs is because we have a close partnership with NVIDIA, and they're working actively to improve that and so forth. Portability across accelerators is important too, especially when you're moving into other deployment environments like an autonomous vehicle or edge applications. And again, this is one of the strengths of JAX and really XLA, is the ability to move between different compute infrastructure, GPUs or TPUs. It doesn't show CPUs here, but that's actually similar as well. This study, by the way, was done by Cohere and MIT. So here's a quote, one of many. We have a long list of these. But the community that's adopted JAX really appreciates the strengths and beauty of it. And this is, I like what he says here. Okay, let's turn now to Flax NNX. So Flax NNX is probably the most important library for you to know. Notice I've been talking about JAX. Flax NNX runs on top of JAX. And it's really the canonical neural network library that you use with JAX. It's not the only one by any means. There's several others. But it's a great one to start with, and we'll see some examples of it. Yeah. Here's kind of a high-level look at the JAX AI stack. And there's the pip install at the bottom. So you've got your hardware on the bottom. XLA is the compiler that we just talked about that converts your Python code into very efficient machine code. JAX runs on top of that. And then on top of that, there's a set of libraries that come with the JAX AI stack, and they're packaged and tested and so forth. 3 of them are there. Flax NNX is the main one that we'll be talking about, but also Orbex for checkpointing, and OptX for optimizations. So creating your optimizers. Here's a more detailed look at some of the tools. So we've got XProf and Metrax for doing evaluation and profiling, VLLM for serving on the right there. The main section in the middle is the JAX AI stack. So it's Flax NNX itself, OptX, and Orbex that we just talked about, Grain is a data loader, and it's designed for loading in distributed environments. So when you're loading shards of data to a bunch of different compute nodes or accelerators, it handles that sort of thing for you, as well as interacts with the checkpointing for that. JAX is an assertion library and really utility library for really creating reliable code, especially in production environments. Really important. Okay, so the goals for Flax NNX, and this is a library that has evolved. We just released this last year, so it has benefited from all this experience. The idea here was to make building networks in JAX simpler, more flexible, and more intuitive for the developer. The intuitive part is important. And we'll see code here in a second. It really aims to streamline the process of creating, inspecting, and debugging your models, building on the experience of earlier JAX libraries, like there was one called Flax NNX. Has anybody used Flax NNX, maybe? No? Yeah. The core concept in Flax NNX is the NNX module. So it's the fundamental building class, it's the base class that you'll use to build just about everything. So when you're creating a new layer, you subclass NNX module. Even optimizers are subclasses of NNX module. Here's an example of creating a layer. So in this case, it's a layer with a random parameter. Very simple. So we've got a dunder init that initializes the class, the instances of the class. And we've got a call method. I mean, this is Python, right? You've all seen that pattern before. One thing to notice is we're passing in a random number generator, and we're doing it explicitly. And the reason that's important and the reason we do that is because you need to manage your random state in order to create reproducible results. Because if you just take some global state that you got somewhere, the next time you run, you're going to get a different result. So this is how we manage reproducibility. There's a whole set of layers that come with Flax NNX, as you might expect. And then, you create your own, or you modify these, or what have you. And of course, we have to do mnist, right? Everybody has to do mnist. That's the link there at the bottom is to the mnist tutorial for Flax NNX. And, we've all done it. It's a great way to get started with a new framework. I'll leave it up there for a second if you want to snap it. All right. So here's, probably some of you know PyTorch, I'm guessing. One or two, yeah? Here's a comparison of PyTorch on the left and Flax NNX on the right for doing the same thing. This is creating a shifted ReLU activation function. So compare that code. Does that look like it would be hard to learn if you already knew PyTorch? Here's another example. So this is creating a simple classifier. And again, we have PyTorch on the left, Flax NNX on the right. Okay, there is a ton more to know about Flax NNX, the JAX AI stack, and so forth. So like I said before, we're moving fast. We're not going to cover everything, and it's going to be a little bit of a blur if this is the first time you've seen it, and probably for most of you it is. Don't worry, I'll point you at a bunch of resources where you can go back in and learn everything else. But we're going to move on now to talking about sharding and distribution, which again is really important for scaling and really getting speed, especially for training, but even in inference scenarios as well. So really, whenever you're working with more than one worker or accelerator, you don't have to be working with 50,000 like we saw earlier. If you're just working with a handful, you have those accelerators because you want to get the most value out of them. That's why you have them. So how do you do that? Sharding and distribution is a key part of that, along with your algorithm itself. So things like flash distribution or flash attention are important. So in order to do that, you need to distribute either your data or your model or both. And we'll talk about that in a second. First, we'll start with data. Well, actually, first we'll start with why you do distributed training. The primary drivers are the sheer scale of models that we're working with today. Trying to fit a multi-billion parameter model onto one GPU or TPU just isn't feasible. So distributed training allows us to break that problem down and distribute it across a number of accelerators, GPUs or TPUs. And JAX deals with this using a paradigm called SPMD, or single program multiple data. Essentially, it makes it look like you're working with one giant computer, and then it handles the fact that you're actually working with many under the hood. So we'll start with the most basic form of distribution, distributed data parallelism, or DDP. So in this case, we are replicating our model onto each of our accelerators. Each of our accelerators has a copy of our model. And then we're going to shard our data and send each accelerator its own shard of data. And then we average those together for our backprop and do the gradient accumulation and move forward. So this is, people have been doing this for a while, and it's great if your model will fit in the memory on your accelerator. But in many cases, it won't. So then you have to start looking at model sharding, and FSDP is probably the most common method of doing that. In fact, FSDP is not just model sharding, it's sharding both model and data. So in this case, each of your devices gets a different shard of your data and a different shard of your model parameters, and they go through the forward pass and do their work, and then they synchronize and they move forward. So in this case, you only need to fit a single shard into the memory on each of your GPUs or TPUs, which is typically a lot more feasible to do. But not always. Sometimes you might have, a really big layer in your model, or you may have really limited memory on your GPU or TPU. And that's where tensor parallelism comes in. So in this case, we're splitting individual layers across devices. So you can think of it as like a bunch of different devices working together to do one huge matrix multiply. And for tensor parallelism, the speed of your I/O between devices becomes really important. So that's kind of the third, and there's others as well. It's not a comprehensive set of approaches to distribution and parallelism. But starting out, JAX gives you, the easy button. You can essentially just give JAX your model and your hardware. It'll go out and discover what hardware you have, and it'll do a reasonably decent job of distributing your model and code and your data and handling things like your all reduce and your all gather. It does a reasonable job of that. So for a first pass, it's a great way to kind of get started and try things out. But it's not going to be as efficient as explicit parallelism. So we'll talk for a minute about how you do explicit parallelism, especially in Flax NNX. The foundation of explicit parallelism in JAX is what's called the mesh. So you can think of it as creating a logical arrangement like a grid of your physical hardware. We typically give names to the axes of this grid, and a common setup is a 2D grid with an axis for data and an axis for mesh, for model. But you can name them, you could have more dimensions, whatever works for you. So here's a code example of creating a mesh. In this case, a 4x2 mesh, because we have 8 accelerators in this case. And that's it. And we give the axes names, in this case, data and model. So you might use this for a V28 TPU, for example, which until recently was available for free on Colab. So thinking about how we use our 8 devices, we have several different choices here. When we created our mesh so far, we had 4-way data parallelism and 2-way model parallelism. But we could just as easily have 2-way data parallelism and 4-way model parallelism, or pure model parallelism, or pure batch data parallelism, sharding only across the data dimension. Yeah, so that's like a one-line change in your code to make those changes of approaches. Once you have a mesh, you use a partition spec to map your tensors to your mesh. And those tensors could be an entire layer. So here's 3 code examples showing both sharding and replication across your dimensions. Where you see none in those second 2 examples, that means we're replicating across that dimension. So so in the spec 2 there, we're sharding across the data dimension, and we're replicating across the model dimension. To use this in Flax NNX, there's really 2 ways to do it, but here's the preferred method, using NNX with metadata. So in this case, we have a tensor. It's of type NNX param. And we're sharding it. We're replicating across the data, assuming we're using the same mesh as before. We're replicating across the data dimension and sharding across the model dimension. Here's an example with a transformer block where we're sharding across the model dimension. And you can see this is actually for a layer norm, so we're doing it for that whole layer. Okay. So, like we talked about a second ago, the reason you do this is because you have invested in accelerators, which are expensive, whether you're buying them and running them yourself on-prem or you're renting them on a cloud, and you want to get the maximum use out of your accelerators. So in order to do that, you're going to do something called roofline analysis. And essentially what that means is you're going to try to keep your accelerators busy. So this again is a deep topic. We're only going to scratch the surface, but I'm going to introduce you to it so you have a feel for what roofline analysis is and why it's important. Oh, helps to push the right button. Yeah, accelerators are expensive, and we want to get the most bang for our buck. One of the reasons we do this is to be able to iterate faster. So if we're going through training runs, whether we're doing pre-training or fine-tuning, we want to be able to iterate fairly quickly. So that means making use of the resources that we have the best way we can and not waiting for data. So this is where roofline analysis comes in. What we're going to do is adjust our sharding and distribution and potentially our algorithm so that we get maximum MFU or model flops utilization, meaning that we're keeping our accelerators busy and not waiting for data. In order to do that, we need to understand how much horsepower our accelerators have and how fast our I/O bandwidth is. And there's different kinds of I/O bandwidth. There's I/O from onboard memory in your accelerator. There's I/O between chips in a cluster, and then there's I/O between clusters. So there's different speeds here, and how you manage that becomes really important. And of course, it's going to be different for every model architecture and for every hardware setup that you have. So you need to go through what you're doing. That's where the flexibility and modularity really becomes important. I should say this is not unique to JAX at all. This is a standard technique for any kind of production AI. So even though we're talking about JAX and Flax NNX, this really is just, I mean, it's an important part of any production AI once you get to scale. Your goal is to reach critical arithmetic intensity, which is fairly easy to understand. What it means is that we're making maximum use of our accelerators and not waiting for data. And what arithmetic intensity is, it's the amount of work we have to do divided by the amount of data we have to move around. So if we can reduce the amount of data that we have to move around for a given amount of work, our arithmetic intensity goes up and we're more likely to be compute bound, which is what we want to be. We want to be compute bound. And the other way around, we're more likely to be I/O bound. So this is a typical roofline plot. And notice arithmetic intensity didn't have a time component, but this does. So we're looking at flops per second, and we're looking at a couple of different cases of I/O here for different amounts of arithmetic intensity. So essentially what you see, if we look at bandwidth number 1 there, is that as the flops per second increases, we eventually reach a roof, the top of the graph, where we can't do any better than that. We've maxed out our accelerators, and that's as good as we're going to do, which is where we want to be. And similarly for bandwidth 2, but that happens a little earlier because it's a little faster, so we get to our top earlier. So this is really kind of what you're looking at when you're trying to take advantage of all your accelerators as much as you can. And it's how we got to results like this one. Doing this kind of analysis and understanding really the hardware that we're dealing with, the I/O, the compute power, the number of flops that we can compute to get to results like this. So this is really, again, where production AI really happens when you're trying to make things fast. So I don't want to sugarcoat this. This is not easy stuff. I mean, this gets pretty deep, and there's a lot of work involved in getting to results like we just had. And we covered a lot in a short time. And I hope if this is the first time that you're seeing this stuff, I've been able to give you a taste of what people are doing in production AI. So then the question is, where do you go from here? Well, we recommend starting with the official JAX AI stack, and there's the pip install at the bottom again, because it gives you a great place to start. It gives you a complete toolkit that you can start with. And then if you want to use a different neural network library, the way that JAX is designed, you can plug a different one in, or a different optimizer library, or whatever it is, a different data loader. But it gives you a great place to start. Start thinking in terms of function transformations when you're coding. So things like JIT, when you want to compile things and make individual functions turn into fast kernels. Things like grad, when you want to calculate a gradient and compose it into a function. Or things like VMAP, when you want to vectorize something instead of writing a for loop. And that vectorization, again, is going to happen in fast machine code. Leverage the ecosystem. So there's a lot of libraries out there. They solve common problems for you. And again, the breadth is really amazing. There's a lot of different fields covered besides AI, but even just in AI, there's a ton of stuff. Most importantly, though, start building. I mean, the way you learn any framework is to start playing with it and using it, porting a model or something from another framework that you have to learn how things work, learning about how to use the debugging tools that are available, learning how to use the profiler and so forth. That's really how you get started with stuff like this. And we think, you know, just like other developers have when they've moved to JAX and Flax NNX, some of you will really begin to love it. Okay, I told you I was going to give you a bunch of resources, so here we go. There's a complete set of slides, coding exercises, and quick references that are available at that link on the top. So there's like, I think there's 12 notebooks with like 5 exercises each, and there's 13 slide decks and so forth. Tons of stuff there. We're going to be coming out soon with some videos, so stay tuned. When I say soon, I think it's probably next week. So we are in post-production right now. Okay, everybody, okay. There is a community on Discord. That's an invite link. So if you want to join the community and you know, get help from other people or just talk about things, great place to do it. There's the docs for 3 of the libraries in the JAX AI stack. The top one is for the JAX AI stack itself, so it has links out to all the rest of them. But yeah, the great resources there as well. Finally, for the stuff that we're talking about for really performance tuning and scaling and doing things like roofline analysis, there is a great ebook available. This was created by the DeepMind team to explain how they do this kind of work. It's a great book. I've learned a lot from it, so highly recommend it if that's something that you want to learn more about. And that's my talk.
Thank you so much. That was awesome, Robert. And we're going to break for coffee now. We'll be back in here starting again in 14 minutes. I guess because it's a coffee break, Robert, if you're up for taking a question or two, we could do a question after you get the selfie. Cool. Well, for anyone whose brain isn't completely melted, who's got a question? Okay, do you want to go ahead and... Oh, we got to get that mic working over there. Yeah. There you go.
All right. Right here. I do have a question. Right here. Yeah. So I think, please correct me if I'm wrong, when JAX was first released, it was mainly targeted for TPUs, but now we have also support for CUDA. And I don't know if it has support for the Apple hardware on the NPS side. But the question, as you are a product manager, is I see some models going to JAX instead of PyTorch. For example, I think Grok 2 was on JAX, and I see that JAX is doing a more modular architecture, so it's really easy to plug in whatever models you want. But we still see the industry going more towards PyTorch, even with the problems that maybe it's getting too bloated because of a lot of things. How do you see the industry right now and the future of JAX maybe trying to move in as a powerful alternative to PyTorch?
I'm not completely sure I understand the question, but are you asking how is JAX moving towards PyTorch?
Yeah, how do you see the industry maybe considering using more JAX over PyTorch?
Oh, PyTorch is huge. It's a huge community. It's actually comparable or bigger than the TensorFlow community, which is still huge, by the way. JAX is much smaller. It was started quite a bit later, and at the beginning, it was really focused towards really high-end developers. So it used, and still does use at the JAX level, something called functional programming, which you may be familiar with. Flax NNX is an object-oriented layer on top of JAX. But Flax NNX is really designed to be a lot more intuitive and developer-friendly. So that we just released last year. And within Google and within large model developers like Anthropic and many others that I can't really mention, there are a lot of people using JAX for really leading edge work. And they were historically using JAX with what was called Flax Linen, which was also a functional approach, and still is. You can still use Flax Linen if you prefer. But they're moving to Flax NNX, so it's a transition.
One more here.
So I had two quick questions. So you mentioned about FSDP and like tensor parallelism. I was wondering if it supports like other types of parallelism, like pipeline and the newer like expert parallelism. And then the other question was, you mentioned about like roofline analysis, but I was wondering if JAX supports like a way to automatically like analyze the topology and whatnot and like do some sort of optimization without having to like manually do this yourself.
Okay, so first question, are there other kinds of parallelism? Yes, there are other kinds, and they are all supported. The flexibility that you saw when we created a mesh and then mapped that mesh to tensors means that we can map that any way we want. So, yeah, pipeline parallelism, expert parallelism, yeah, absolutely. And the second, what was the second question?
Sorry, the second question was, I'm trying to remember myself.
Does JAX support like automatic optimization?
Oh, yeah. Yes, well, that's what we talked about. So that's the easy button option that we talked about. It does do automatic optimization, and it makes a best attempt. Like it's able to go out and find out, how many accelerators you have and things like that. There's limits to it. I mean, it doesn't really know how fast your bandwidth is from your HBM, things like that. But it makes a reasonable attempt at it. And it gets you, a reasonable result.